Today I'm going to tell you about a simple scheduling policy that has nearly optimal response time with unknown job sizes. I'm Zeev Scully, a PhD student at CMU, and this is joint work with my advisor Moharkal Balter and Alan Schellerwolf. So today's talk is going to be about the MG1 queue, a classic single server queuing model. So I'll start by telling you what that is. We've got one server which can serve one job at a time, and a queue that can hold any number of waiting jobs. So this is what a job looks like. We're going to represent it as a test tube, where the height of the test tube is the job's size or service requirement. That's how much time it needs to be served for before it completes and exits the system. So we're going to represent serving a job as filling the test tube with water. So a job's age is the progress we've made so far. That is the height of the water, how much time it's been in service already. And then the rest of the job is its remaining size. So we've got jobs randomly arriving over time, specifically at random times and also with random sizes. So we've got a job size distribution, X, from which each job size is independently drawn. We have Poisson arrivals at rate lambda, and this gives the system a load, rho equals lambda times EX. This is the long run fraction of time the server is busy, and it should be less than 1 so that the system is stable. So this is the MG1 queue, and today we're going to be talking about scheduling in this queue. So the scheduling policy is the algorithm, depicted here as a robot, that decides at every moment in time which job to serve. And it does so preemptively. So at any moment, it can decide to interrupt the job currently in service and start serving a different job. And when it does this preemption, there's no delay or loss of work. So that's the MG1 queue with preemptive scheduling, and we're going to be looking at response time of various scheduling policies. So a job's response time is the time from when it enters the system to when it leaves, complete. Now this includes both the time serving the job itself, that is filling it with water, but it also includes time the job spends waiting in the queue, which is affected by the scheduling policy. So our focus in this talk is going to be designing scheduling policies that minimize mean response time. So let's talk about what the state of the art in scheduling to minimize mean response time is. Suppose we know each job's size. How should we schedule to minimize mean response time? Well, the idea is that we want to get a job out of our system as quickly as possible, because whichever job we can finish the quickest, that's going to give us fewer jobs in the system, which corresponds to lower mean response time. And the policy that gets jobs out of the system as quickly as possible is SRPT, shortest remaining processing time. This always serves the job of least remaining size. And it's simple to show that SRPT is in fact optimal among all policies for minimizing mean response time. But it requires knowing each job size. So what if we don't know job sizes? What do we do now? Well, we can't schedule using remaining size because we need to know job sizes for that. But we do know the job size distribution. And so based on that overall job size distribution and each job's age, we get for each job a remaining size distribution. So we can't schedule according to least precise remaining size, but we could schedule according to least expected remaining size. This is a policy called SERPT, for shortest expected remaining processing time. We're going to call it SERPT, and it serves the job of least expected remaining size. So SERPT seems like a great idea, right? It seems like we're naturally generalizing SRPT to the case where we don't know job sizes. Surprisingly, SERPT actually isn't optimal for minimizing mean response time in the unknown size setting. Instead, that honor goes to the Gittins policy. So the way the Gittins policy works is more complicated than SERPT. What it does is it looks at each remaining size distribution and solves an optimization problem to come up with a number called that job's Gittins rank. If you've heard of Gittins index, it's the reciprocal of that. And so once it's come up with these numbers, these Gittins ranks for each job, it serves the job of least Gittins rank. So here's the situation we're in for unknown job sizes. We have an optimal policy, Gittins, which is actually very complicated to compute. And we have a much simpler alternative, SERPT, for which there's unfortunately no guarantee on its mean response time. There's no guarantee that even though SERPT seems like a great idea, we don't know what its mean response time is compared to Gittins. So what we really wish we had is a policy that was as simple as SERPT, where we had a provable guarantee on its mean response time, that it was somehow close to optimal, close to that of Gittins. So the way this work started is we actually tried to prove that SERPT was this magic policy. We tried to bound the mean response time of SERPT compared to that of Gittins, but we actually weren't able to finish the job. What came out of that effort, though, was a new policy that achieves both of these goals. It's called M-SERPT. It's a new flavor of SERPT. And I'm going to tell you later about what M-SERPT is and its response time guarantee. But first, I'm going to give you some background on SERPT and Gittins so you can understand the context around M-SERPT. So, what is SERPT? How does SERPT work? So, SERPT serves the job of least expected remaining size. That is, it uses the job size distribution to estimate the remaining size of each job. So let's walk through what SERPT looks like for this job size distribution, where jobs are either size 1, 6, or 14, each with equal probability. So we're going to represent SERPT for this job size distribution using what's called a rank function. A rank function maps each job's age, that is the amount of time it's been served so far, the height of the water so far in the test tube, to a rank. This is a number representing a job's priority, and we're going to use the convention that lower is better. So, SERPT is always serving the job of least expected remaining size. So the rank function of SERPT has a job's rank at age A be its expected remaining size, conditional on having reached age A. So remember, lower is better, so lower remaining size is better. That's exactly what SERPT does. So let's walk through what the rank function looks like in this example. When a job enters the system for the first time, it's at age 0, so its expected remaining size is 7. And then, as we serve the job, its expected remaining size goes down a little bit because we're making progress until we reach age 1. What happens at age 1? Well, if the job is size 1, then it's done, exits the system. So if it hasn't exited yet, that means the job isn't size 1, so it must be 6 or 14. So the conditional expected remaining size is now 9. And then something similar happens at age 6. We've got these rank jumps at ages 1 and 6. And so this is the rank function of SERPT for this example. And just to be super clear about what this means, let's walk through how SERPT works when you've got these two jobs in the system, one at age 3.5, one at age 6. Who does SERPT serve? The one of lower rank. So we're going to start by serving this job at age 3.5 until it reaches age 6. Suppose that it's actually a big job, size 14. So at age 6, its rank will jump up. And now we actually have two jobs tied at rank 8. So what happens now? We're going to follow the convention of breaking ties, first come, first serve. So this means that whichever of these jobs arrived first in the system, we're now going to serve that one. So that's a crash course in how SERPT works and in how rank functions work. Now let's talk about Gittins. Gittins follows the same overall outline in that it's expressed using a rank function and that rank function is based on the job size distribution, but the rank function in question is a lot more complicated. Here's the formula. But after doing all this computation with this formula, we get a rank function that looks superficially similar to SERPT. So it seems like SERPT is capturing something along the lines of what Gittins is doing, though with different details. And so what we kind of tried to do is we tried to show that SERPT was kind of close enough to Gittins in its rank function decisions. And that's where we ended up getting the idea for M-SERPT. So let me tell you now about what M-SERPT is. M-SERPT is also described using a rank function. And its rank function is defined in terms of SERPTs. Specifically, the M-SERPT rank at age A is the worst SERPT rank between ages 0 and A. Pictorially, what this means is if this is the SERPT rank, then the M-SERPT rank is a version of the SERPT rank that never goes down. It's monotonically increasing. That's actually what the M stands for. M-SERPT is monotonic SERPT. So let's see what M-SERPT looks like on our favorite example. Remember that the M-SERPT rank function is the worst SERPT rank function between ages 0 and A. And so this is what M-SERPT looks like compared to SERPT. It's the monotonic version of SERPT. So we've now seen what M-SERPT is, right? It's a new policy that's as simple as SERPT, specifically defined in terms of the same rank function, but it has a provable guarantee on mean response time. Specifically, we show that M-SERPT's mean response time is within a factor of 5 of Gittins's. Now, you might be thinking, 5, that's not that small a number. And I have a few things to say about that. So the first is that this number is actually smaller at lower loads. I'll show you a chart at the end of the talk. The second is that this is actually the first constant approximation ratio for mean response time shown for any policy in the MG1, other than, of course, Gittins itself. So this is a significant technical contribution to be able to do this. And finally, it turns out that M-SERPT is often a lot better than a factor of 5 away from Gittins. So on our favorite example, our 1,614 example, all three of SERPT, Gittins, and M-SERPT have very similar performance. And this actually prompts a question, a couple of questions. It looks like SERPT and M-SERPT are both doing really great, really close to Gittins. And admittedly, this is just one example, but we've actually tested lots of examples, and we found that M-SERPT and SERPT are consistently pretty close to Gittins. And so the questions this raises are, well, why did we have to invent M-SERPT? It seems like SERPT is doing great. Why doesn't SERPT work? Why can't we get the same proof working for SERPT? And the second question is, where does this factor of 5 come from? It looks like we're doing a lot better than a factor of 5. So in the rest of this talk, I'm going to be able to answer both of these questions. Why we needed to invent M-SERPT, and why we get a factor of 5 as its approximation ratio. And to answer both of these questions, we're going to use a response time decomposition that's been used to analyze many scheduling policies over the past several decades. It's very simple. It breaks up response time into two pieces, T equals Q plus R. So remember that T is response time. Q we can think of as queue-based delay. So if I'm a job, my queue-based delay is the delay due to jobs that I see in the queue when I first enter the system. R I can think of as my run-based delay. So this includes my own size, that is the time I spend in the server, plus delay due to me getting interrupted while I'm in service, perhaps by new arrivals. So these are the two parts of response time, Q and R. And we're going to use this decomposition to answer both of our questions. So let's start by comparing SERPT and M-SERPT. And we're going to try and see why we needed to invent M-SERPT, where M-SERPT is better than SERPT. So let's start by asking, what's the difference between SERPT and M-SERPT? Well, the difference is in the name. It's the M. M-SERPT is monotonic. Rank never goes down. SERPT, on the other hand, it has these valleys in its rank function, where the rank function dips down. So let's ask, how does one of these valleys affect Q and R? Right? Compared to M-SERPT, does SERPT's Q go up because of the valleys, or does it go down? What about R? So let's start by looking at Q. Suppose that I'm a small job. So this is my size. My worst ever rank is this orange dotted line under both M-SERPT and SERPT. So this means that any job whose rank is above this orange dotted line, it's dead to me. I don't care about it at all. It will never bother me. So under M-SERPT, any job that's at a sufficiently large age is dead to me. I never have to worry about it again. Under SERPT, though, its rank function has these valleys. And so in particular, if at the moment when I arrive into the system, I see a job with age in this interval, that job gets to be ahead of me for some time. And so that will contribute to my queue-based delay. And so, in fact, SERPT has larger queue-based delay than M-SERPT. Now let's talk about R, the run-based delay. So for this, we're going to take the opposite perspective. Now let's suppose I'm one of those big jobs, and that this is my size. So under M-SERPT, my rank only ever gets worse with age. It's very unforgiving, right? My rank goes up a little bit, it's at least that high forever until I exit the system. SERPT, on the other hand, offers an opportunity for redemption, right? My rank can go down again after it's gone up. And in particular, in this valley, as my rank is going down, my priority is improving, and so I get interrupted less by arriving jobs. And what this means is that E of R SERPT is actually at most E of R M-SERPT. So SERPT beats M-SERPT in the R category. And so what we have is actually a complicated trade-off between SERPT and M-SERPT. It's not clear which one's better. One has better Q, the other has better R, and you can actually construct job size distributions on which SERPT beats M-SERPT and vice versa. So the important thing for our goals is we're trying to prove a guarantee over all job size distributions. So we're looking for universal bounds on EQ and ER for both SERPT and M-SERPT. And what we're able to do is we're able to bound all four of these quantities except EQ SERPT. That's the tricky one. And that's why we haven't solved the problem of whether SERPT is a constant factor approximation for mean response time. And this is why we had to invent M-SERPT. So, now that we've seen why we need M-SERPT at all, let's see where this factor of 5 comes from. So that comes from the two steps of our proof of M-SERPT's approximation ratio. So the first step has to do with bounding the Q part. We have that EQ M-SERPT is less than 2 times EQ Gittins. This is the first major step in our proof. The second major step bounds the R part. It says ER M-SERPT is at most EQ M-SERPT plus a slowly growing function of load. And so EQ M-SERPT we can bound using our first step, right? 2 EQ Gittins. And it turns out that this slowly growing function of load is at most the mean response time of SRPT. And at this point, we can see where the factor of 5 comes from. EQ Gittins is at most ET Gittins because Q is just part of response time. So we've got 2 ET Gittins over here, 2 ET Gittins over there, and then SRPT has optimal mean response time among all policies, so there's another ET Gittins over here. And so we've got 1, 2, 3, 4, 5 total ET Gittinses. So the mean response time ratio between M-SERPT and Gittins is at most 5. So that's where the factor of 5 comes from. So we might be wondering now, is there an opportunity to get a smaller factor? So it turns out that the first step of our proof is tight. There's no way to get a smaller factor over all job size distributions for the Q part. We have an example that attains this factor of 2. However, the R part has a loose bound, so we think there's some opportunity to improve here. We haven't actually observed any tight example for this second step. And in particular, we conjecture that the true approximation ratio of M-SERPT might be as low as 2. So, to summarize, today we talked about a new scheduling policy called M-SERPT, which is the first scheduling policy with both a simple rank function and a constant approximation ratio for mean response time compared to the optimal policy that is Gittins. Specifically, we showed a constant approximation ratio of 5, and the constant's actually better at low load. Here's the full expression, and here's what it looks like on a graph. And what I want to draw your attention to is the fact that the mean response time ratio is below 3 up until pretty high load of 8/9. So I want to thank you for watching this video. If you have any questions, please feel free to email me at zscully@cs.cmu.edu. I'd love to hear from you. Thanks again for watching.